We take a circle, radius r, is at an angle theta from the horizontal. We see a right triangle with the hypotenuse r. The adjacent side becomes the x-coordinate of the point on the circle, and the opposite side becomes the y-coordinate. From the Pythagorean theorem, we can combine these sides to get x squared plus y squared equals r squared. We take this equation, we divide by r squared. The r squared cancel, and we arrive at our first trig identity, sine squared theta plus cosine squared theta equals 1, where x over r is cosine and y over r is sine. We can instead divide by the other two sides. We can divide by y. We can divide by x, and we can even divide by y. We cancel the commonalities, and we arrive at our other two trig identities, 1 plus tangent squared and cotangent squared plus 1. These three identities together are what are known as the Pythagorean identities because they were derived from the Pythagorean theorem. What's more about these identities is they make use of the 6 trig functions, cosine, sine, tangent, secant, cosecant, cotangent, where the ratios equal as such. If you take a look at these ratios closer, you can see that the first 3 trig functions are essentially the inverse of the last 3 respective trig functions, so we can relate them as such, where cosine is equal to 1 over secant, sine is 1 over cosecant, and tangent is 1 over cotangent. Now, since x over r is cosine, then x becomes r cosine, and similarly y becomes r sine theta. One way to think about this is to think of the r as like a scale to the cosine and r as a scale to the sine, where we can see this idea better if, for a moment, we let r equals 1, then x becomes cosine theta and y becomes sine theta. Here, now that r equals 1, it's simply cosine and sine, but if r was to be greater than 1, we could imagine this whole right triangle being scaled up by that factor r. So the hypotenuse will be scaled by r, and similarly the x side will be scaled by r, and the y side will be scaled by r. Hence why the x side, the cosine, gets scaled by r, and the y side, the sine, gets scaled by r. Okay? We generate a rectangle. We inscribe a right triangle as such that one of the corners of the triangle is at a corner of the rectangle. We let the angle at that corner be beta, and we let the hypotenuse be 1. So adjacent becomes cosine beta, and opposite becomes sine beta. By existence of this triangle, we see another triangle in purple. We let the left angle be alpha, and now we can see that the adjacent is cosine alpha times some scale r, where r is the hypotenuse, based on our earlier discussion. Similarly, the opposite is r times sine alpha. Now here r is simply cosine beta, because that is the hypotenuse. So plugging in, we get this. Now let's take a look at the top right triangle. The bottom angle becomes alpha, simply because this line is perpendicular to this line, and this line is perpendicular to this line. And whenever that's the case, this angle must equal this angle, alpha. And further, since the hypotenuse of this triangle is sine beta, we say that the adjacent and opposite of this triangle are scaled by that factor sine beta. So we get sine beta cosine alpha and sine beta sine alpha. Now let's take a look at our final triangle. We see that the top right angle is alpha plus beta. And this is because this line is parallel to this line. And since this big angle, alpha plus beta, and this angle share the same line within those parallels, that means they must equal. So this must be alpha plus beta. Now since the hypotenuse is 1, we can say that the adjacent is cosine alpha plus beta, and the opposite is sine alpha plus beta. And now that we have all the edges defined, we can start equating them. Let's focus first on the vertical edges. So we can see that the sine beta cosine alpha plus cosine beta sine alpha term equal sine alpha plus beta. So we get our first relation. And now let's take a look at the horizontal edges. We say that cosine alpha plus beta times sine beta sine alpha equals cosine beta cosine alpha. So we get our second relation. We want to isolate for cosine alpha plus beta, so we rearrange it. And we arrive at our sum angle property for sine and cosine because we are summing two angles, alpha and beta. Let's clean this up, move this here. I rearrange the terms so the alpha will come before the beta. Now we can derive for the difference property from this if we let beta equal negative beta. So then it equals cosine alpha sine of negative beta plus sine alpha cosine of negative beta. Sine negative beta equals negative sine beta because it is an odd function based on our earlier discussion. And similarly, cosine negative b becomes cosine beta. It is an even function. Plugging in, we get this. Now that plus negative looks kind of ugly, so let's clean that up. And let's rearrange it so we have the negative term after. And we can get a similar derivation for the cosine. And we arrive at our difference angle properties for sine and cosine. Now we can take the ratio of these two, the sine and the cosine, sum and difference, and we can arrive at the tangent sum, and difference. Okay? But these are in terms of cosine and sine. What if we want it in terms of just tangent? Well, for the top one, for the sum, we can readily do that if we divide the numerator and denominator by cosine alpha and cosine beta. Okay? Like terms cancel. Now sine beta over cosine beta becomes tangent beta, and sine alpha over cosine alpha becomes tangent alpha, and this simplifies to the following. And we can do a similar simplification for the difference case to arrive at this. And if we pair these back up with the sine and cosine, we get the sum and difference for our first three trig functions. And we can extend these derivation to get the remaining three trig functions as follows. Now, for a moment, let's focus just on the sine sum angle. If we let beta equals beta plus gamma, plugging that in, we can see that this equals sine alpha times cosine beta plus cosine alpha sine beta plus gamma. Well, cosine beta plus gamma is the cosine sum angle, so we have this formula from our previous discussion. And similarly, sine beta plus gamma is the sine sum angle, so we have this formula. Plugging it in, we get the following. Now we're going to substitute for sine and cosine, and we get this. And this right here is the sum triple angle for sine. Triple angle because we are summing alpha plus beta plus gamma. Okay? Now, going back to the sum angles, if we were to let beta equals gamma, then we can see that we arrive at the double angle. It becomes 2 alpha. Okay? For sine to alpha, we can see that it has sine alpha, cosine alpha repeating, so it can simplify to 2 cosine alpha, sine alpha. For cosine to alpha, we can see that it has cosine times cosine, which becomes cosine squared, and we have sine times sine, which becomes sine squared, so it simplifies to the following. And lastly, for tangent to alpha, we see we're adding 2 tangents on the top, and we are multiplying 2 tangents in the denominator, so we simplify to the following. Now, we can further visualize the sine and cosine to alpha by bringing out an isosceles triangle. Okay? Left and right are equal to 1. We can split this triangle into 2 right triangles. Since it's an even split, the top angles become alpha. And then this implies that this angles, the left and right angles, will become pi over 2 minus alpha. From this, we can see that the middle leg is cosine alpha, and the 2 base legs are sine alpha. Now let's generate another triangle as such, in blue, where now the hypotenuse is 1, and the bottom angle is pi minus 2 alpha. Why is it pi minus 2 alpha? Well, because this is 2 alpha, and this is pi over 2, and all three of these have to add up to 180 or pi. So, subtracting this and this, we would arrive at this. And further, the side adjacent to 2 alpha becomes cosine 2 alpha, and the side opposite becomes sine 2 alpha. Now the question is, what is this angle in purple? Well, it is this angle minus this angle. So, it is pi over 2 minus alpha minus pi over 2 minus 2 alpha. This becomes the following. The pi over 2 cancel, and we are left with alpha. So, we get alpha. And by this, we can see that the middle leg equals cosine alpha times some scale r, where r is the hypotenuse of this triangle. And by virtue of this, the opposite side becomes r sine alpha. Now, what is r? Well, the r is the length of this base. It's 2 of these sine terms, so it becomes sine or 2 sine alpha, because we're adding them. Plugging that in for r, we get this. Now, sine times sine becomes sine squared, so plugging that in, we simplify. Okay? And now we have defined enough of the edges to start seeing how our identities play a role in this triangle. Okay? So, let's start with the right edge. So we say that cosine 2 alpha plus 2 sine squared alpha equals 1. So we get our first relation. Recall that earlier we said that sine squared alpha plus cosine squared alpha equals 1. That was a trig identity. So plugging that in, we get the following. We can cancel the sine squared alpha, and we can drop the 2. And now we can see that this, what remains, is the cosine double angle. And further, if you focus on the middle leg, we can see that 2 sine alpha cosine alpha equals sine 2 alpha, which, rearranging, we see that it is our sine double angle. So we have visualized our sine and cosine double angle from this triangle. Going back to the sum angle. So far we saw that we went from a sum to a product, but what if we want to do the reverse? We want to go from a product to a sum. Well, more precisely, a product ratio to a sum angle, because these are sum of angles and these are product of ratios, the trig terms. So let's do that for 4 possible cases: sine alpha, sine beta, sine alpha, cosine beta, cosine alpha, sine beta, and cosine alpha, cosine beta. For reference, I left the sine sum angle and the cosine sum angle formulations on the top. If we take a look at the sine sum angle, we can see that we can isolate for sine alpha and cosine beta, essentially get towards this, and we can also isolate for cosine alpha and sine beta, essentially get towards this. So in doing that, we have this and we have this. And further, we can take a look at the cosine sum angle, and we can isolate for cosine times cosine and sine times sine. So this will essentially work towards this, and the sine alpha sine beta will work towards sine alpha sine beta. So we get our other 2 isolations. Now these 4 equations are not enough to just plug them in right away to this, because the right side isn't a complete sum angle, because we still have a product term. For example, we want just sum terms, but we also have a product term. Same for this, and same for this. So we have to go one step further and somehow plug in for these, so we have another sum or difference, okay? But we can't do that just with the equations we have, because if you take a look at it, this is right here. If you plug this in right here, plug this back in, then you'll just end up with the same term, and it'll be redundancy. And you'll find the same issue that if you plug in this equation into this product, you'll run into that same redundancy. So to sort of solve that, we could bring in some variation, bring in the cosine and sine difference angle, where now we can repeat the same process. We can isolate for our 4 products. And now what we do is we match the first equation from our first 4 to the first of our last 4, okay? And in doing so, we can see that if we add these 2 equations together, the cosine alpha and sine beta cancel. So now we have it solely in terms of the sum angle, just a sum angle, which is what we wanted. And dividing by 2, we arrive at our identity for sine alpha times cosine beta. And we can do a similar trickery to get the other 3. So we match those 3, okay, with their respective equations, and we have this. In the top case, sine alpha sine beta, we add them so we can cancel out the cosine alpha minus cosine beta, and we arrive at this. For the third case, cosine alpha sine beta, we subtract it, so it's a negative plus a negative and a negative, so we can cancel the sine alpha cosine beta, and we arrive at this. And similarly, we arrive by canceling sine alpha sine beta at this for the cosine alpha cosine beta. Dividing the 2 over, we get our remaining 3 identities. Now, for a moment, if we take out the sine times sine and the cosine times cosine, and we take the ratio between them, then we can arrive at tangent times tangent, where now if we cancel out the 2's, it simplifies to this. And now we have 5 identities for product ratio to sum angle, where technically it is sum and difference, because we see we have sum of angles and we also have difference of angles. Now we saw product of ratios. How about sum of ratios? So sum of these ratios in terms of sum of angles. How will we get that? So we bring our sums over. We go ahead and generate a right triangle. The left angle is alpha. The hypotenuse is 1, which implies that the adjacent is cosine alpha, and the opposite is sine alpha. We then generate a second right triangle sitting at the top of it, where the left angle is beta. Hypotenuse is also 1, so adjacent and opposite become cosine and sine beta, respectively. Now, if we extend a midline from the bottom point to the topmost point, we can see an isosceles triangle, because the left and right sides are the same, they equal 1. So this further implies that the left and right angle are also the same. So delta on the left and delta on the right. Now, if we split this isosceles triangle into 2 right triangles, we can see that the 2 base legs are cosine alpha, Or sorry, cosine delta. I keep making that mistake. And further, we can generate two right triangles as such, where now the hypotenuse of them is cosine delta. And we say that the left angles are a new variable gamma. The bottom leg, or the adjacent to gamma, becomes cosine gamma times some scalar r. But r here is cosine delta. So, plugging that in, we get this. And similarly, the opposite side becomes cosine delta sine gamma. And we can arrive at the same values for the other triangle because it is the same triangle. Now that we have these edges defined, we can go ahead and start equating some of them. You probably noticed that by now it's a common theme, equating these edges. So, without further ado, we can see that cosine alpha plus cosine beta equals to 2 cosine delta cosine gamma. So we get the following relation. And focusing on the vertical edges, we see that sine alpha plus sine beta equals to 2 cosine delta sine gamma. So we get this relation. By the way, I may have said gamma or alpha when I'm supposed to say like delta. Just know that, pay attention to what's on the screen, not my voice. I've been saying a lot of alpha, gamma, delta, so it's all mixed up in my head. I apologize. Anyways, going along with all the delta, gamma, beta, alpha lingo, we see that we want the right side in terms of alpha and beta, so we have to solve for delta and gamma. So let's go ahead and do that. First things first, we see that alpha equals delta plus gamma, so we get this relationship. Now, what about this blue angle at the top? Well, that becomes pi over 2 minus beta, and so we can further solve for this purple angle at the top. Well, that becomes pi over 2 minus gamma. If you care to figure that out, similar to the derivation that we did earlier. So, seeing that purple plus delta equals blue, we get the following relationship, where the pi over 2 cancel, and we arrive at delta equals gamma plus beta. Sorry, gamma minus beta. Where now we equate the delta with the delta, and we get the following. Alpha minus gamma equals gamma minus beta. We can now simplify for the gamma, and we arrive at this. And we can plug the gamma back in, and isolate for delta, and we arrive at this. And now, we can plug in for delta and gamma, and our right side is in terms of alpha and beta. And we align them up, and we have our cases for sine plus sine and cosine plus cosine. What about the other three? I'll leave that to you to try that out. Think you can find it? Give it a stab. Okay? So, moving on. To recap, so far we covered sum angle to product ratio, where we took the sum of angles and we got the product of ratios. Next, we took a look at product ratio to sum angle, where we took the product of ratios and we got to sum or difference of angles. And lastly, we took a look at sum ratio to sum angle. We took the sum of the ratios, the trigs, and we got to the sum of the angles. The alpha minus beta, alpha plus beta. Okay? And all of this, we saw the common theme of arriving or starting from angles. But what if we want to work with ratios alone, from a ratio to a ratio? For example, from tangent theta to sine theta. So let's focus on that. How would we solve that? Well, let's bring out a right triangle with the angle theta. Adjacent side is x, opposite side is y, and hypotenuse is r. From this, we can see that tangent theta equals y over x, and sine theta equals y over r. Since we are going from tangent to sine, if for a moment we say that tangent theta equals some capital R, representing its ratio, then we can solve for sine solely in terms of that ratio r. Okay? So, if we let y equals r, then x will equal 1, because y over x has to equal r. Using our Pythagorean theorem, isolating for lowercase r, we get this. And now plugging back in for capital R, the x and y, we get this. And now we have the lowercase r in terms of capital R, and we have the x and y in terms of capital R. We can plug in for sine theta equals y over r, and we get this. And now we can plug back in for capital R, the tangent theta, and we get this. And this right here is our tangent ratio to our sine ratio. Okay? And similarly, we can get an equation for tangent to cosine, where the derivation is very similar. It comes out to this. So, tangent to cosine, the formula is like this. And since in total there are 6 possible trig functions, we can actually tabulate all possible cases from the 6 trig functions to the 6 trig functions, the ratio to the ratios. Where if you look at the diagonals, you can see that you're going from the same trig to the same trig. So let's not count those. And further, you can see that the first three are the inverse of the final three. So whenever we are going from a trig function to its inverse, for example, from sine to cosecant, we generate the inverse. So for example, if we're going from sine to cosecant, it becomes 1 over sine. This right here is a typo. It should be 1 over sine. I apologize. I promise there are no more typos. Fingers crossed. And we can generate all the other combinations as such. Now, there are some patterns you might be noticing. For each column, for each trig, each of the 6 trig, we can see that one of the outcomes is a radical. Another one of the outcomes is 1 over a radical. The other is trig term over radical. And finally, we have trig term over a radical. Sorry, we have radical over the trig term. Okay? Isn't that quite neat? And further, since the first 3 are the inverse of the last 3, we can see that they're each other flipped. So for example, this row is this row flipped. Cosine, radical 1 minus cosine is 1 over radical 1 minus cosine, and so on and so forth. Now let's get back to our original case of tangent to sine. This is what our formula we got. Now technically, I know we're saying that we're going from ratio to ratio, but actually it's kind of more like an angle because we still have the theta sneaking in there. So how do we actually get it in terms of the ratio? We just don't have the theta at all. Meaning, how do we get it in terms of some r? Well, in order to do that, then we have to work with the inverse tangent, okay? And now we say that the theta has to equal that inverse. So technically now our starting point is sine of inverse tangent r. So now our function becomes this. And going back to our table, our tabulation, we now have this, where now the diagonals become r. Because, for example, sine of sine inverse r is just r, because you're undoing it. And similarly for cosine of cosine inverse, and so on and so forth. And if you look closely, if you match it up with the original table, let's match it, you can see that the only thing that really changed are the trig terms got replaced by the ratio r. Okay? So this is another way of kind of doing the same procedure. And that right here pretty much completes the video on all these identities. To end this, let's mention some honorable identities, some honorable mentions. So we have the power reduction, and then we also have the half angle, where if you look closely, the half angle is very similar to the power reduction. Right now, instead, we took the radical of this and got this, and we reinterpreted theta to be theta over 2, so then 2 theta dropped down to a theta, okay? And further, we have triple angle, and then we have sum of the inverse trig, where before we were summing the trig, now we're summing the inverse trig. Next, we have complex exponential, and we have the inverse complex exponential, okay? And these are all possible by Euler's formula, e to the I theta equals cosine theta plus I sine theta. More on that later in a different video. It's a whole another topic. And finally, we end with Lagrange's trig. I'm sure I butchered that pronunciation. You can correct me. And that right there ends it.